Okay, now we've got the understanding of the energy needed to keep in the air, we can work out how it applies to an aeroplane. An aeroplane works, as we've said, by deflecting the air downwards. The actual physics of how this works is quite complicated, but basically the exact shape of the wing and the angle of the wing deflects air downwards that passes close to it, and it's that downward motion of air that keeps the aircraft in the sky. So to be specific, I've picked a particular plane, one of the most common you see in the world today, an Airbus A320. I've picked the latest Neo version. Now this cruises at about 10 kilometers altitude, where the density of air is about 1/3 that of sea level, so about 0.4 kilograms per cubic meter. The plane, when loaded, has a mass of about 70 tons, range of about 6,000 kilometers, cruising speed of 840 kilometers per hour, which is 230 meters per second. It's got a wingspan from tip to tip of 36 meters. Okay, so it weighs 70 tons, so we're going to need an upward force of 70 times g, which is about 7 by 10 to the 5 newtons, to stop one of these planes falling out of the sky. And that must be supplied by diverting air downwards. This is the weight of 700 tons, so you could push 700 tons of air down per second at 1 meter per second, or you could push 1 ton of air per second down at 700 meters per second, or any combination of these two. Which combination do we actually use? Well, we can try and estimate it. My gut feeling is that only air that passes fairly close to the wing is going to get deflected down. So I'm going to guess that if it's about within 1/5 of the wingspan above or below the wing, then it will get deflected down. So if you've got a wingspan out here, you take 1/5 of that, air either that far above or that far below will get deflected down, whereas the air further away will just be left in peace. So what that means is there's this rectangular prism of air in a given second which is going to get deflected down. It's going to have a height of plus or minus 1/5 the wingspan, so 14 meters up and down, and a width equal to the wingspan of 36 meters. And as it's travelling at velocity v in each second, that means that the total mass deflected down is about 48 tons per second, which is not bad at all. It's a lot of mass of air you're directing down. We don't think that air weighs a lot, but this is a lot of cubic meters, so it weighs a lot in this case. So this deflected air is called the downwash. How fast does it need to move downwards? So we need m dot v equals mg, and that gives you a downward speed of about 15 meters per second, which is 50 kilometers per hour. So that's actually quite a fast downward flow of air, but it's still less than 10% the forward speed of the plane. And you can work out the power needed to accelerate 48 tons per second up to a speed of 15 meters per second, and that turns out to be about 5 megawatts. So just to keep the plane in the air, well, at cruising altitude, you need about 5 million joules per second, 5 megawatts. And this is what's called lift-induced drag. This is the drag you need to have because it's keeping your plane in the air. It actually gets lower as you go faster, because if the plane goes faster, more air collects close to the wing, and can get deflected down. And so if you can deflect more air at a lower speed, you need less power. So this is an interesting thing. The lift-induced drag is worse when the plane is travelling slowly and gets smaller as it gets faster. So now we can look at the total energy needed for a flight. So to begin with, you'll need some potential energy to climb to cruising altitude and kinetic energy to reach your cruising speed, half mv squared and mgh. Then when you're at your cruising altitude, you need to overcome the drag and provide the lift. Then on the way back down again, well, I guess you get some of your potential energy back, but you might need air brakes or something to burn that away so you can land safely. So you don't generally get the energy back. There's no way you could drive dynamos to get the energy back on the way down. So let's look at it. First of all, climbing. And planes typically cruise at about 10 kilometers altitude, so mgh about 7,000 megajoules to get up there. Kinetic energy, half mv squared, is about 2,000 megajoules. So all in all, about 10,000 megajoules to accelerate and reach cruising altitude. But now let's compare that with the energy needed actually to sit at cruising altitude. So energy used, force times distance, or power times time. Now you're going to need to contribute two things. First of all, there's a lift-induced drag. This is the deflecting the air down to keep yourself in the air, which needs some energy, which is going into pushing the air around. So we've seen this about 5 megawatts. And that goes down as your speed gets higher, because you're pushing more air down at a lower speed. Then there's also going to be parasitic drag. This is a drag we've already talked about when talking about cars and bicycles and so on. This is actually just pushing an object through the air, like the fuselage and the propellers and so on. And that's complicated around planes. They are very streamlined. The density of air is low up there. But parasitic drag also, as we've seen, goes up as v squared. So as you go faster and faster, there's going to be more and more parasitic drag. And generally planes are designed to operate in this sweet spot in the middle, where the lift-induced drag has fallen down and the parasitic drag hasn't taken off yet. And wings are designed so that at cruising altitude, just below the speed of sound, they're at the sweet spot. So let's assume we've got about equal. So we've calculated about 5 megawatts of lift-induced drag and probably about the same in parasitic drag. So it's total power of about 10 megawatts. Now another way to calculate this is to use a lift to drag ratio. This is the ratio for a plane flying. There'll be a certain amount of lift that keeps it in the air, but a certain amount of drag that's just trying to slow it down. And it turns out that for modern airliners, the lift to drag ratio is about 18 to 1. So to lift every 18 newtons of aircraft weight, you need 1 newton of drag force. And using this, you get about a thrust of 38 kilonewtons needed to support an A320. So force times speed is about 9 megawatts from this, which is actually very close to what we estimated, about 10 megawatts. Okay, so that's good. It means the standard lift to drag ratio more or less agrees with our calculation of 5 megawatts for lift-induced drag and about the same for parasitic drag. So if we need 10 megawatts of power for a 6,000 kilometer flight, that's 7 hours. So power times time gives you about 2 by 10 to the 11 joules, which is actually 20 times more than the energy we worked out before to climb, which is only about 10 to the 10 joules. So the energy use of the plane is dominated by cruising, overcoming the drag. Energy needed is about 2 by 10 to the 11 joules. How much energy does it actually use? Well, an A320 has a fuel capacity of about 25,000 litres of fuel, about 20 tonnes of fuel, 36 megajoules per litre. So that's about 9 by 10 to the 11, roughly 10 to the 12 joules. So overall the plane is about 25% efficient. So it burns 9 by 10 to the 11 joules. It requires only 2 by 10 to the 11 joules. So divide 1 by that. It's about 25% efficient. So why is that? Now when we talked about cars, we immediately thought that they've got a low efficiency because only the Carnot limit. And that is the case here, but that's not the entire story. So aircraft engines are heat engines and are limited by the Carnot limit, just like car engines and power stations. But when tested on the ground, the best modern aircraft engines are like 40 or 50% efficient, much more than this 25%. So that explains half the gap, but we're still going to need something else to explain the other half of the gap.